Welcome to the AMD Spartan UltraScale Plus SCU35 Evaluation Kit, Introduction and Features Demonstration. In this video, we will introduce the Spartan UltraScale Plus FPGA family, explore the Spartan UltraScale Plus architecture, introduce the SCU35 Evaluation Kit, and examine its board components. Let's briefly define what a gate array is and what it means for a device to be field programmable. A gate array is just a regular arrangement of logic gates. Field programmable means that the device can be programmed any number of times, at any place, any time. So, field programmable gate arrays, or FPGAs, are semiconductor devices that are based around a matrix of the programmable logic gates connected via programmable interconnects. AMD FPGA families have evolved from the 7 series, which introduced a unified architecture with RTX for low cost, Kintex for mid-range, Vertex for high-end, and Zynq SoCs combining ARM processors with FPGA fabric to UltraScale, which improves scalability, routing, and support for high bandwidth interfaces like PCIe and 100 gigabit Ethernet. Finally, UltraScale Plus adopted 16 nanometer FinFET technology for better power efficiency, advanced security, enhanced DSP capabilities, and optimized transceivers for high-speed communication. Now let's take a closer look at the AMD UltraScale Plus architecture. UltraScale Plus devices leverage the ASIC class architecture built on a 16 nanometer FinFET process, delivering better power efficiency, performance, and area optimization while maintaining compatibility with UltraScale 20 nanometer devices. They retain the proven programmable logic PL architecture found in existing UltraScale devices, including the core logic, routing, clocking, block RAM, and DSP slices, making IP migration from 20 nanometers to 16 nanometers straightforward. UltraScale Plus devices are available across a wide range of AMD devices, such as the Vertex, Kintex, RTX, Spartan, and Zynq families. Furthermore, the Zynq UltraScale Plus MPSoC adds an integrated processing system, PS, with ARM Cortex A53 and Cortex R5 cores, combining high-performance processing with flexible programmable logic. AMD Spartan UltraScale Plus FPGAs offer high I/O density, providing 3.5 times more I/O per logic cell than previous Spartan devices, low power consumption, and robust security features. Built on the 16 nanometer process node, they include hardened IP for DDR and PCIe on larger devices, improving interfacing efficiency. The AMD Spartan UltraScale Plus architecture is designed to maximize efficiency and flexibility by integrating a comprehensive set of fundamental building blocks. At its core lies the programmable logic, the flexible fabric for custom circuit implementation. Surrounding this are diverse I/O blocks, HDIO, HPIO, and XP5IO provide versatile interfaces, while MIPI D-PHY offers a soft IP solution for high-speed mobile interfaces. Memory resources are robust, including dedicated block RAM for high-performance storage, as well as large, high-density UltraRAM, complemented by external LPDDR 4X or 5 support for high-speed memory. Key hardened acceleration components comprise high-speed transceivers for serial links, PCIe Gen 4 IP for high-performance host or peripheral interconnectivity, and dedicated DSP blocks for high-throughput arithmetic. The architecture also integrates essential system elements, such as comprehensive clock management blocks for precise timing, dedicated security features for design protection, and the Microblaze 5 soft processor for embedded intelligence, all collectively providing an optimized solution for diverse applications. Having explored the key architectural building blocks of the Spartan UltraScale Plus FPGA, let's now shift our focus to the SCU35 evaluation board. The SCU35 evaluation board is a comprehensive hardware platform engineered to facilitate the practical implementation and validation of the advanced capabilities of Spartan UltraScale Plus FPGAs in real-world application scenarios. The SCU-35 evaluation board is designed for evaluating and developing applications using the Spartan UltraScale Plus XCSU 35P device. It emphasizes high I/O count, low power, and security features for industrial and healthcare applications. There is one board model available, EKSCU-35G, which is the AMD Spartan UltraScale Plus evaluation kit. The SCU-35 evaluation board features the Spartan UltraScale Plus XCSU 35P FPGA in the SBVB625 package. To support configuration, the board offers three onboard methods: a USB to JTAG bridge, a JTAG pod via a flat cable connector, and Quad SPI or QSPI. Power management is handled with USB-C control. For connectivity, the SCU-35 supports multiple I/O expansion interfaces, including Arduino, HSIO, Microbus, Raspberry Pi Hat, and PMODs. The board also integrates 8 MB of HyperRAM, an MII 1000 Ethernet interface for networking, and extensive GPIO resources such as DIP switches, push buttons, RGB LEDs, and UARTs. Clocking sources include a 100 MHz LVDS system clock and a 200 MHz HyperRAM clock, along with design-dependent HSIO clock inputs and outputs. Debugging and monitoring are supported through HPIO, HDIO headers, Sysmon, and power telemetry over I2C. Additional components such as an accelerometer, EEP-ROM, an optional cooling fan, and status LEDs further extend functionality. The SCU-35 evaluation board features a PCB with dimensions of 5.512 inches by 5.512 inches with a thickness of 0.06412 inches and an assembled thickness of 1.379 inches. It is designed for lab environments, operating within a temperature range of 0 degrees Celsius to 45 degrees Celsius and tolerating humidity levels from 5% to 95% non-condensing. The board requires an operating voltage between 9 volts DC and 20 volts DC. Having reviewed the physical specifications and operating conditions of the SCU-35 board, let's now examine the core device that it hosts. The SCU-35 evaluation board is populated with the Spartan UltraScale Plus XCSU-35P FPGA device, which integrates powerful programmable logic, PL, along with diverse peripherals within a single device. Additionally, the device can be configured to integrate a Microblaze 5 processing system. The SCU-35 provides 64 megabits of external Infineon HyperRAM memory to enable software applications that are too large to fit in the FPGA block RAM. This interface is connected to HPIO Bank 47. Use of this HyperRAM memory device in a Microblaze 5 system requires an IP core that is provided by Infineon. The SCU-35 board includes a 64 kilobit I2C compatible EEP-ROM organized as 8K by 8 bits. It has two addresses associated with it. Address hex 50 is used to access the memory array, and address hex 58 is used to access the identification page. The SCU-35 board includes a 3-axis linear accelerometer at I2C address hex 18 targeted for industrial applications. It features two configurable interrupt outputs connected to the FPGA. The SCU-35 board provides 3 UART interfaces connected between the FPGA and USB to Quad UART bridge device through level shifters U8, U9, U12, and U14. The port assignments are as shown. Let's now go over the different expansion interfaces available on the board. The SCU-35 board features an Arduino Shield interface connected to HDIO Bank 68. It provides 14 digital I/O, 6 analog I/O, 2 power pins of 3.3 volts and 5 volts, and 2 ground pins, with all I/Os supporting a single-ended line rate of up to 250 megabits per second. Reverse current blocking eFuses are provided for overcurrent and reverse current protection, allowing a maximum current draw of 0.5 amps from the 3.3 volt rail and 1 amp from the 5 volt rail. The VIN pin is unconnected, so Arduino shields that supply power are not supported. The SCU35 board includes a single-width HSIO standard port based on the SYSOG standard. All HSIO I/O signals, except I2C on bank 67, are connected to HPIO bank 47, and the differential pairs operate at a 1,500 megabits per second line rate. The interface provides power pins for 1.8 volts, 3.3 volts, and 5 volts rails with load switches for overcurrent and reverse current protection are enabled by the signals on bank 6, allowing a combined maximum current of 2.0 amps. Since the board does not include a smart VIO controller, all HSIO I/Os are limited to 1.8 volts. The SCU35 board provides 2 Micro eMicrobus expansion interfaces for use with Micro eClick boards connected to HDIO banks 65 and 66. Each interface offers 11 digital I/O, 1 analog input, 2 power pins, and 2 ground pins, with the analog input linked to the Sysmon XAD C pins on bank 66. All I/Os support a single-ended line rate of up to 250 megabits per second. The interfaces are powered by a 3.3 volt rail with a load switch for overcurrent and reverse current protection, and are enabled by the signals on bank 67, allowing a maximum current draw of 1.0 amps. The SCU35 board includes 4 Digilent PMOD interfaces connected to HDIO bank 66. Each interface provides 8 digital I/O, 2 power pins, and 2 ground pins, and the connectors are positioned to support dual-wide PMOD boards. All I/Os operate at a single-ended line rate of up to 250 megabits per second. The interfaces are powered by a 3.3 volt rail with a load switch for overcurrent and reverse current protection, and is enabled by the signal on bank 68, allowing a maximum current draw of 1.0 amps. The SCU35 board provides 2 Raspberry Pi Hat expansion headers connected to HDIO, banks 45 and 46. All I/Os on the Hat interface support single-ended line rates of up to 250 megabits per second, with higher speeds for lower voltage standards. The 3.3 volt rail supports a maximum current of 0.5 amps, and the 5 volt rail supports up to 1.5 amps, with load switches providing reverse current protection. For all expansion interfaces on the SCU35 evaluation board, including Arduino Shields, HSIO, Microbus, PMODs, and Raspberry Pi Hats, it is critical to note that the XCSU35P FPGA I/Os are not 5 volt tolerant. Designers must ensure that the FPGA bank I/O voltage strictly matches the requirements of the assigned I/O standards for each interface to maintain signal integrity and prevent device damage. The SCU35 board implements a 1000 megabits per second Ethernet interface using an MII Ethernet MAC IP. The FPGA connects to a MII PHY, which routes signals to the RJ45 Ethernet connector. The PHY is set to address hex 01 with auto negotiation enabled and is reset via the ENET RSTB pin, controlled by system power good signals and FPGA I/O, which are accessible through push-button SW2. The RJ45 connector includes 2 LEDs managed by the PHY, whose behavior can be customized through the MDIO MDC interface. Next, we'll look at how we can power the board. The SCU35 board uses a USB-C port as its primary power input. When connected to a valid 9 to 20 volts, 3 amps USB-C power supply, the orange LED illuminates to indicate proper input power. The PD Sync controller negotiates voltage and current and delivers regulated power to the main system. To generate the required core and auxiliary voltages, the board integrates power management ICs and regulators from monolithic power systems. The overall status of the power system is indicated by the SysPG LED. The board includes a cooling fan connector that can be controlled using a PWM signal. Fan speed is autonomously adjusted through PWM signals based on the FPGA temperature. The fan runs slowly and quietly when the device is cool and accelerates as the temperature rises, becoming acoustically louder to ensure adequate cooling. A controlling software application must be created to monitor the XCSU35P FPGA temperature and drive this logic. An FPGA PWMIP is required in the user design. The board provides a fan controller header to permit control by the Spartan UltraScale Plus device. The SCU35 board supports two boot modes, JTAG and QSPI, which are selected using the mode configuration header. The header pin settings for each mode are as shown here. For JTAG mode, set the J35 header pins to the JTAG configuration as indicated in the mode selection table. A JTAG connection can be established either through a USB to JTAG or USB UART interface, connected through USB micro B JTAG UART port, or through a JTAG pod flat cable connector. After setup, power cycle the board or press the reset push button to complete initialization. For QSPI mode, configure J35 to the QSPI setting as shown in the mode selection table. Then store a valid boot image in the onboard QSPI flash memory. Finally, power cycle the board or press the reset push button to start the boot process. Spartan UltraScale Plus, FPGA's power, a diverse range of applications. In industrial environments, they enable automation, robotics, and smart infrastructure through high I/O density and low power consumption. In medical systems, these devices deliver real-time processing and reliability for advanced patient monitoring and surgical solutions. For wired and wireless networking, they provide the performance required for 4G and 5G infrastructure, board control, and connectivity. In data centers, Spartan UltraScale Plus technology ensures efficient board management and storage acceleration, offering scalability and energy efficiency for large-scale computing. These capabilities highlight the versatility, scalability, and energy efficiency of Spartan UltraScale Plus devices across a broad spectrum of high-impact application domains. To summarize, the Spartan UltraScale Plus FPGA is built on advanced 16-nanometer FinFET technology, delivering low power consumption, high I/O density, and robust security features. It ensures seamless connectivity and rapid multi-platform prototyping by supporting a wide range of interfaces, including Arduino Shield, HSIO, Microbus, PMODs, and Raspberry Pi Hat. To facilitate development, components such as 8 megabytes of HyperRAM, 1000 Ethernet, and USB-C power management are integrated, alongside standard tools like RGB, LEDs, switches, push buttons, and dedicated debug headers. For booting, users can configure JTAG or QSPI through the mode configuration header. Ultimately, the Spartan UltraScale Plus FPGA combines energy efficiency, extensive connectivity, and design flexibility, making it an excellent choice for diverse embedded, industrial, and medical applications.